cool. So let me, just before I take any questions or anything, I want to show you this little spreadsheet that I made, just so you can actually know that this stuff can be made with Excel. Enable editing. So Grace had come by to talk to me, consult with me about the bonus problem. And if you looked at the bonus problem, you know it's about finding Pythagorean triples with a certain mechanism. And that mechanism involves complex numbers. So Grace, I think Grace's question was, is it just, do I just have to do trial and error and crank them out? And I was like, pretty much. So, and yeah, she was like, that sounds not good. It's like, well, let's see if we can do it in Excel. So Excel can actually handle complex numbers. You just have to do things the right way. So my first step was to actually just create this little matrix of some complex numbers. Let me show you how I did that. So if you just type here, if you just say equals complex, and you give it two arguments, the real and the imaginary part, it creates the complex number for you. So this is complex with real part 1, and then imaginary part, this A2. And don't worry about that dollar sign right there. That's to keep the reference static for the row, or excuse me, for the column. If you're more interested in why I'm doing that, I'm happy to share that with you. But once I have that, I just put 1, 2, 3, 4, 5 across here, and 1, 2, 3, 4, 5, 6 down. And notice that I can actually just extend this as much as I want now. That's what's one of the beauties about Excel. So if I just move that to the right, yay, it automatically creates that next column of numbers, and I could do that down here. So over on the right, the first row, straight across from each of these numbers, are the corresponding moduli squared. So for example, 1 plus I has a modulus squared of 2. And all I'm doing here is, look at how I'm actually doing it. I'm taking the imaginary product, so just the product of complex numbers, of the conjugate of that number times itself, which gives you the modulus squared. That was actually one of your homework problems that you had to do. To find z squared modulus, you just take z times z conjugate. So I just did that here. So this is the modulus of that, that's the modulus of that. And then underneath I squared it by just taking complex product, probably. Let's see what we have there. Yeah, imaginary power. You can raise an imaginary number to the second power. I did. You could do any power you wanted. And literally just cut and just like copied that all down. And so I can come over here and start looking for Pythagorean triples. The really nice ones, 3, 4, 5. I can just read off real, imaginary, modulus squared, 3, 4, 5. This one is 4, 6, 10, but that's just twice this one. So part of the problem was not doing multiples of old things we've done. Here's a new one, 8, 15, 17. Like, that's a weird one, right? But you can just read them right off here. So just now grab through here and find your favorite Pythagorean triples. Here's 10, 24, 26, but that's actually 5, 12, 13, which is right there. There's that one. And there might be, oh, that's pretty, this is one I wouldn't have guessed, 20, 21, 29. So just kind of a cool way to solve that problem. I wanted you to just see that if you're super motivated Excel-wise, and I hope that you are in some ways, you can get into Excel and do amazing things. So is there anything I can help you with? I think because we had a homework, but like it's due today, but I can still answer questions about it. Is everybody okay? All right, yeah. New homework up. That homework is in the calendar because my handwriting sometimes isn't the best. But let me write it up here on the board so we also have it here. And we're going to do as much as we can today, and I'm going to stop at 3 and let you do the quiz, which should not take very long. I made it pretty chill. So for next Wednesday, if you could do this over the weekend, please read 3.1. If you haven't, or if you started, finish that up. There's stuff in there I'm not going to just say in class. We'll use it, but there's some definitions and things in there that you should read, because even if you hear them twice, that's a good thing. So read 3.1 and then start on 3.2. This is where things start to get weird. So you want to prepare yourself for that, right? So you could just read 3.2.1, the first section there. But this is when we start talking about inverting things around circles, and it's very counterintuitive and weird. And the more you see of it, the better you will be, the better we'll all be. So we'll start that next week for sure, maybe even Monday. Your homework, which ideally do next Wednesday. That's the ideal, but up till Friday, because I know I will end up doing that anyway, so why not? Why pretend like I'm someone I'm not? So the homework would be 3.14 pi, 3.15, 3.16, 3.18. I feel like there's one of these I wanted to modify. Hold on, I might be changing that to the 73.111. Let me look at my book, because I did that right while I was waiting for y'all. Yeah, 3.18. That is the one. No, I want you to do 3.17. Sorry, we're gonna do 3.18 today. So 5 problems. And these will be, things are getting more and more interesting as we move forward. Much more geometry in here. Moving things around, visualizing things and so forth. All right, so we are gonna talk today for a while about transformations in the complex plane. So I'm gonna get some notation. Let's talk notation and let's talk terminology, basic stuff, because not everybody in here has had logic and proof. In fact, a lot of people have not had logic and proof in this class. So let's talk about it. This is describing a function. So this is the name of a function. I'm just going to go very basic. Function name here. This is the domain. This is called the codomain. This is the collection of inputs. This is the collection. This is not necessarily all the outputs, but it's where outputs live. And that will change for us from time to time about what D is going to be. So let's get some definitions here. A transformation, a function, let's just say f, from some domain into some other domain, we'll just say those are the same, is 1-to-1 if what? Somebody want to tell me definition of 1-to-1? Lou's got his hand up there, but does anybody else step in? Yeah, give it a shot, Ella. Yeah.
There's an output for every input, and it's unique.
Okay, hold on. I gotta think of what you said there. There's an output. There's a unique output for every input. So that would actually be a function. That's a function is that every output has a unique every input has a unique output. So something like this is not a function where I don't have a unique output. And I think I know where you're going with that, but the unique was on the wrong part there. But we can flip it around, because that was basically the thing in reverse that we want to say. Do you know what I want to say? Do you want to? Oh, Blue, tell me what you're thinking.
So like if you had like f of A is equal to f of B, then A equals B.
Okay, so yeah, so this is what Ella was getting at here, and it was just a twist of language that made it not quite there. So if when the outputs are the same, that means the inputs had to be the same. And this is, I think this is what you were getting at with the uniqueness kind of. Is that the only way we can define it? No, is that it? Is the answer to that question? Can somebody tell me the contrapositive of that statement? What do I mean by contrapositive?
When outputs are different, the inputs have to be different.
Yeah, there we go. So the contrapositive is, so if you have an implication, you say if P, then this Q follows, that is logically equivalent to the contrapositive, which is if not Q, then not P. So this is called the contrapositive of a statement, of an implication. And so we can take this one, so or if A is not equal to B, then f of B is not equal to f of A. Giving myself mixed up. So in other words, what we want is this to not happen. So this would be bad if I have an A and a B, and they both went to the same place. So this is not 1-to-1. That would be if f of A equals f of B, not 1-to-1. Yeah. So if I know a certain output, it only came from one place. It has a unique input for each output. All right, cool. What about, we got one more term here. So a function f from D to D, some set into another set, is onto if what? What does onto mean? What's up, Blue?
So it's like if for all the inputs, you're using up the whole codomain, which is to say that the range is equal to the codomain. So for any element in the output D, in this case, you can find an element in that first D that it's mapping from.
Exactly. If you want to hit something over here, there's something over here that hits it. So is onto if for every output z y in the codomain, the output space, there is an input in the domain. So this symbol is element. Here, I'm sorry, I'm doing some pseudo mathematical writing here. There's an input in the domain such that an input, call it x, such that f of x equals y. In other words, i.e., we can hit everything in the output space. The codomain. So as Lou said, the range is equal to the codomain. The range is everything you can hit. And that's okay, you don't need to know all that terminology. What are some other words for one-to-one? I almost said it. One-to-one, what's another word for one-to-one? Starts with an I. One-to-one. Oh, it's related to invertible, but it's not. But it does have an N next. There we go, injective. Fancy words, some nice fancy math words. What about onto? What's a fancy word for onto? Yes, who said that? Say that louder.
Surjective.
Thank you. Surjective. Just some fancy words. If a function is one-to-one and onto, what do we call that? A bijection, exactly. So let's put that up and then we can move on. Just a little bit of review, or maybe the first time hearing these things. If a function is one-to-one and onto, it is called bijective. Injective and surjective. If that happens, it also has an inverse. We can find the inverse function. Such a function has an inverse. And it has a special name in our class. And in MT441, with our book, we call it a transformation. So transformations are just nice functions. They're easy to work with. You can find an inverse function, all good. And honestly, you will probably never think about these things, but I need to talk about them so that we can at least know what a transformation is. So if you're all kind of like, what the hell, I don't know about this, don't worry about it. It's cool. You won't need this to actually understand any of the stuff that's coming forward. So any questions or clarifications or things I left out that you think should be put in there?
So all transformations are bijective.
Yeah, I like that. That's just a nice summary. Yeah, beautiful. Thank you, Christian. Okay, so let's look at some special ones, and that's basically the rest of the stuff we're going to talk about today. Special transformations. And then we're going to build stuff with them, and it's going to be lots of fun. Special transformations. The first one is called a linear transformation. And that is a function, z, that takes a complex number, z, multiplies it by a complex number, so a is complex, and adds a complex number to it. Really simple, about as simple as you can get. You're multiplying by a constant and you're adding a constant. What do these look like? Back in back in the day, back when you had this kind of stuff, what does that look like?
Exactly. Yep.
Line, straight line, right? So it's a straight line. There's no, the thing here is you only have one dimension of input. You've got this x-axis, that's your input, and you've got one dimension of output, that's your y-axis. For us, things aren't quite as pretty because this t is going to take every complex number in the plane and turn it into a new complex number. And we don't know where, because it depends on what t looks like. But our goal today, before we leave here, before 3 p.m., is to basically understand everything about these geometrically. What is happening? I want to picture what this is doing to the plane, and that's where the fun comes in. So let's start off with the simplest one. So do we need any condition? If this thing's a transformation, so let's make a little note here. Note t of z equals az plus b is a transformation only if what? There's one little condition that I haven't mentioned, because we want 1-to-1 and onto. What would be bad? And I'll just give you the hint. If A is 0, this is not a transformation, because everything gets crushed to B. Does that make sense? So we need A to be non-zero, and everything is cool after that. Because otherwise, so else, T of Z just looks like this, and it crushes the entire complex plane into a tiny little point over here, B. And that's not 1-to-1, that's infinitely many to 1. We don't want that. So it crushes C to B. We don't want that. We want our whole plane back when we're done. So that's just one little note. Let's see where I wanted to, because I kind of did this in a very gradual, let's start off chill. So some special case, just to get some intuition. This is going to be if a B is 0, sorry, if B equals 0. And then we'll move on from there. So we have T of Z just equals AZ. So there's a couple of things going on here. It's not just multiplying by 2. It's not just stretching everything, because this A is a complex number. So if A looks like this in polar form, we actually have a couple of things happening here. So let's actually put some parentheses in here and look at that. So the first thing I could think of is, what does this do to Z? What does that do to Z?
Gonna rotate it.
It's gonna rotate it, and let's make sure we see that. So this part is just a rotation. If Z is, let's say, rho e to the I phi, so that's its length, that's its angle, then this thing looks like this, R e to the I theta times that guy. And I'm going to group together those two things. So we've got rho, phi. I'm going to pull that out there, and then I add the arguments. So notice that this just adds theta to the angle of the input. So this right here is rotate Z by theta. So there's a rotation. This out in front is just scaling. So out here, we're going to scale by a factor of R. Let's make a couple little notes about that scaling so that we gain more intuition and we can just see things without having to think about them as much. So that R, if R is between 0 and 1, R is a contraction. If this number here is like a half or 3/4 or 7/8, we have a contraction, a shrinking. If R is bigger than 1, if R equals 1, then size stays the same. And if R is bigger than 1, we have, what's the opposite of contraction? Expansion? Yeah, I guess so. Bless you. So let's just take a quick example and look at it. So suppose that T of Z equals, let's just do square root of 2 plus square root of 2i times Z. Let's start with that. So what is this gonna do? What is this doing to every complex number that I bring in? To understand it, I would first convert this to polar form. So this is, and you'll probably believe me, I think, if I write this. This is 1e to the pi over 4I times z. Tell me if that sounds legit. Just that 45-degree triangle nestled in the first quadrant. So this thing rotates by pi over 4 counterclockwise. So this is counterclockwise rotation by pi over 4. And now I understand this map. So for example, if I asked you, what is the image of the set, and let's draw a little picture here. So this is going to be in the complex plane. I'm going to fill that all in, the set S that looks like this, and that's 1 plus I right there. And that's supposed to be a square. So if I asked you, take every point in here, run it through this transformation, what comes out? If I understand its rotation by 45 degrees, I can just draw my new picture, Ella Jova. I feel like you got some. Do you have a question?
Maybe later.
Okay, cool. Okay, good. Just trying to make sure everything's cool. So where does 1 plus I go? It goes up to the imaginary axis. Right? And there's no scaling. How long, what is the distance right there between, what is that distance from there to there? Root 2, right? That's root 2. So when I move this thing up, that 1 plus I, so this is t of 1 plus I up here, becomes square root of 2I. Because I want it to have the same length. That's my new diagonal. And then this point here, this is just good old 1. 1 is going to go to, well, it might help to look at the map. If I let z be 1, I just get out square root of 2 plus square root of 2I. So we get it right here. So this is t of 1, which equals square root of 2 over 2 plus root 2 over 2I. And then where, somebody help me out, where's this other point? Just use symmetry and just basic geometry. What is this coordinate here?
Negative root 2 over 2 plus root 2I, or root 2 over 2I.
Yeah, sounds good. Basically straight across from this one, everything's the same distance-wise, it's just got a negative for its real component. Does that sound cool? Not bad, right? So understanding that if I have a transformation, I should go here to gain understanding makes sense after seeing this. Now there was no scaling, but if there had been, let's actually take a look at the scaled version. If and let's twist things up here. So again, if t of z, now I'm going to change it a little bit. I'm going to put a 3 root 2 over 2 plus root 2 over 2I z. So not only does this rotate by 45 degrees, but it expands everything away from 0 by a factor of 3. So this here is rotate counterclockwise by 3, and then stretch everything away from the origin by a factor of 3. Stretch away from 0 by a factor of 3. So let's play this game again, but this time I'm going to start with just the unit disk. Good God. But the unit disk, pretend that's the unit disk, please. Nice and filled in. La, 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 la. Could you please draw, and let's call that D, because it's a disk. Could you please draw T of D for me? Take a moment. what is T of D gonna look like?
When it says
Yes.
rotate counterclockwise by 3, is
Uh,
that supposed to just
Should,
be
no, thank you, Ella,
45?
yes. The rotate counterclockwise, thank you, ma'am. That should not say that there.
Grace caught that.
By 45 degrees is what I should have said. I was looking at the, thanks. Good call. Does that sound better?
Yeah.
Yeah, that was weird. Thank you. Yep. Yep.
Yes. It's a circle, right?
Yeah, exactly. Yeah, yeah.
Rotate. Oh,
What does this look like if you rotate it around the center?
the same, but they're just so it isn't like the unicorn is just gonna be and that's it.
Trust your intuition. It's good. That's good. But it's good to check too. So what are we rotating by? What happens if I rotate that circle around its center? Same. So the rotation doesn't show up anyway.
Just good.
Yeah. Exactly. That's just like three. Yeah. Does that make sense? Cool. How's it going, Morgan? Yeah, so there's no shifting going on. So it's literally, so it takes the circle and rotates it first, just around the center.
Yeah.
So it doesn't move, and then we scale it by
Okay.
3. Does that make sense? Yeah, yeah, so it kind of just grows.
Because I was doing the stretch away and then I.
Yes, yeah, yeah. Does that make sense?
Yes.
Oh, it's gorgeous. Yeah, solid, most solid. Yeah, however you want. You spin a circle around its center, doesn't matter how many degrees, it still looks like the same circle, and then we stretch everything away from the origin by a factor of 3, so that's just 3i, 3 minus twice I, and minus 3. And then fill in the center, right? Still got all the guts and stuff in there. Cool, not bad. Let's see, what other little thing did I want to talk about? Now I just want to have fun. Now I just want to have fun. So, I want to help you on one of your homework problems, actually a couple of them. You're asked to build transformations that do certain things. And this is the fun stuff. So let's practice a few things together. So construct a transformation that, good lord, a transformation that rotates stuff about not the origin but a different point. So z not equal to 0 by theta. We'll just say theta. Then you can pick your favorite units, degrees or radians, what you want on theta. So let's look at what we have at hand. Oh, and I didn't, oh shoot. Sorry, hold off on that one. Come back to that really quick, because I did forget about the one other thing. If I have T of Z equals Z plus B, so I forgot to actually talk about this part here. And this would have done what Morgan, what you got there. This is just a translation. This literally moves us in the direction of B. So this is translation by B. So let me give you a quick example. If I have T of Z equals 1 minus I, Z plus 1 minus I, then what that's going to do is take each point and move it over by 1 and down by 1. So it will take the point Z and move it over 1 unit and down 1 unit. And that would be T of Z. So we have translation. So it's pretty straightforward, unlike the rotation and scaling stuff, which are kind of all smashed together. Cool, I need that for this. Because what I want to do is figure out how to spin around this thing. But we don't know how to do anything except spin around the origin. So here's what we're going to do. We're going to say, here's my point Z. I want to rotate that sucker by theta, whatever that is, around Z naught. So step 1 is move the whole problem to the origin. So we're going to translate first by minus Z naught and get ourselves to the origin. So move to the origin. And I'm going to keep track of each of these. So I take Z minus Z naught. And at that point, here's my picture now. This was the old Z naught, because Z naught goes to 0. And then here's my Z minus Z naught. So just shifted everything there. Pick up the whole picture and move it down. Now I can rotate. So now I'm just going to multiply by e to the I theta. And that's going to rotate me by theta. So step 2 is now rotate this by theta by multiplying by e to the I theta. So let's keep track of that, because that's all in parentheses. So at this step, I've got e to the I theta, Z minus Z naught. What do I want to do to get back to where I started? Add Z naught back on. So then we shift everything back. So step 3 is add Z naught to this to get back to the start, back to original situation. So I'm going to write that out, and that is going to look like this. E to the I theta, Z minus Z naught, plus Z naught. And there, my friends, is my transformation that does what I want. And I would take this, because I would just want to do this, and put it in that AZ plus B form. So this is totally kosher, and in fact, probably more informative if you look at this, because you can see what happens here. You see the translation, then the rotation, then the translation back. But let's expand it out, so it's e to the I theta Z. And then let's do a couple steps here. And so I'm going to group these two together and just factor out that Z naught. And do a little bit of funky rewriting just to make it look pretty. I like to have my negatives inside if I can tuck them in. But you know, your mileage may vary and your tastes may vary as well. But here we have it. There's our beautiful thing that does what we want. Really cool, right? So think about the step-by-step process that took. And let me ask you to do it now, in part of a first step toward a homework problem that I gave you. Indeed, that was some sort of hoot of excitement that I heard out there. So, construct, and I'm going to get you started. I'll put the problem up. Construct the formula. Ooh, hold on. One last thing. There is one thing we can't do that we're gonna really wanna do with this thing here. So T of Z equals AZ plus B can do lots of things. It can rotate, scale, and shift, but it cannot flip over things. Can't flip over things. And when I say things, I mean lines here, essentially. To do that, we use Z conjugate. So the only way you can flip is through conjugation, and the only thing you can conjugate is across the x-axis. So this takes Z and flips it over the z-axis. Let me convince you that we can't do this with the other form. So for example, let's say I had this triangle here. It's a weird, really weird little triangle, but I'm trying to make it tall and thin like that. The only way I could turn that triangle into this triangle is through flipping. I cannot rotate, scale, or translate that thing into that one. No way. So these have what are called different orientations, and this preserves orientation. And this reverses orientation. So when you want to flip something, you've got to do a conjugate. And you can only conjugate over the x-axis. Please keep that in mind for your homework problem. And let's do this one together. But I'm going to let you just work on this a bit first. So here's the problem I'd like you to please find. Find a formula for T of Z that flips everything over a horizontal line. And I'm going to draw the horizontal line right here. So here's my complex plane. Let's just say this is the line, and that is just y equals k right there. And there's the z you could start with if you wanted. Think, it's a little puzzle. I'm going to run to the restroom. Think about shifting and whatever else might be needed in the appropriate order. I'll be right back. got it? Think we got some? Let me see what you got. You think you got some? This, not yet. No. Okay. Hint shift first. Yeah. So kind of. That's actually close, but not quite right.
No?
Yeah, because that line there, that K is a real number. So if you subtract off a real number, you're actually doing a left-right shift. So that's close. But then, and also, if K is a real number, the conjugate of K is not K, is equal to K. So those would cancel.
Wouldn't K be an imaginary number? Since Y is
Well, it
equal
could
to
be. Well, it could. The way I've written it, yeah. So that's it's a matter of, it's a little ambiguous here, but we usually write our complex numbers like this, Lou. So I can see why you're thinking that. But
Yeah.
what I'm saying is that Y is a real number.
Okay.
So everything along this line here would be of the form Ki, which is the subtlety there.
Okay.
See if this works anymore.
Yeah. Let's see, C2.
There's like a line.
Yeah, where's your conjugate?
Yeah,
So you're
like that makes
you're
sense.
rotating,
Like, kind of
so
stuck
you're
on the side.
rotating, which would not actually be a flip. Your thing would not turn that triangle into that triangle. Do you see what I'm saying?
Yeah.
I
Yeah.
shifted the line down, so I said.
Would this work with like doing individual points?
So let's see, what are you doing here? So you can see you're shifting.
I'm really just applying this to the last like equation where you're
Yeah.
rotating about a point, but then like maintaining X so that like for wherever you have Z, you have like a point that's like directly
Yeah.
beneath it.
Yeah, and so, can I see
Yeah,
that too real
of
quick?
course.
So, you're actually shifting by a whole lot, because this would cancel out your X on this Z immediately, and it would cancel a lot of things, so it would actually smash you over to here first. And then when you add it back, this might, I don't know, yeah, it's my word, but there's no flipping.
Okay.
You have to conjugate.
Okay.
You
That
gotta
makes
do a
sense, yeah.
conjugate, yes. That's pretty close. It's not quite right, but it's really close. That's pretty close too, but it's not quite right either. How we doing?
The more you explained it, the more I lost it.
Okay, all right. Let's go through this. Let's go
Good
through
for us,
this.
you know, we were almost there.
So the first thing I'm gonna do is shift everything down to the x-axis. To do that, I subtract off Ki. So I was thinking this was something like this, y equals 3. That means all the imaginary parts of all the points on that line are 3. So everything on there would be 3i for its imaginary part, and have a different x part for the real part. But let's just say, keep it like it was. So the first thing I'm gonna do is subtract off Ki from every number. So I'm gonna take z, and I'm gonna subtract off Ki. Now what that gets me is down to, it moves the line I'm flipping over down to the x-axis, and it makes my z keep the relative position, keep its relative position to that line I'm gonna flip over. So that's step one. Now I'm gonna conjugate. So you were close, you're so close, but then you didn't put everything back, ladies. That was the problem. So now flip. And so I'm gonna take z minus ki, all of that conjugate, and that flips me. So now I'm underneath, but I didn't start here. I have to shift everything back up. So to put myself back, I put plus ki. And now I'm back to where I started. And we can actually simplify this and actually gain a really interesting insight. This is one of the things I've been really loving. So let me stop there, and before I do anything, should I explain more? Can I talk that through more? Is that making some sense more? Is that feeling a little less insane?
Yeah, I had it partially correct, and then you explained something, and I was like, I don't know.
Okay, good, that's good, sorry. I'm glad you're back. Glad you're feeling good. Any questions about that? Your homework problem is going to be to do this around any vertical line, which will involve And just remember, you can only flip horizontally. There's a little tip. You can only do it over the x-axis, so if you've got to do it like this, you might want to make it like that at some point. So this, I'm going to use this property that if I have z plus w conjugate, that's z conjugate plus w conjugate, so this piece becomes z conjugate minus ki conjugate. That's just a pure imaginary number, plus ki, that just riding along. What is the conjugate of ki? So if I had this number, we'll just put it here, 0 minus ki. What's the conjugate of that? 0 plus ki. So it turns that into a plus, and we get 2 ki. And that's our transformation. So that's actually kind of cool, because I can look at it in a different way. This says to flip over this line, you could just take the conjugate first, take you all the way down there, and then add 2k to get back up. So kind of a cool insight that I don't think is obvious at all. It's certainly not obvious to me. I'm assuming some of you probably have way better geometric intuition, but kind of cool. Yeah? Just somebody say it's cool.
It's super cool.
Yeah, okay, there we go. Great. Thank you. Let's call it a day. Please start on all that stuff so we can talk on Monday, because we're not done, right? If you wouldn't mind getting out a piece of paper. If you would like me to go get you paper, I will. You would like paper?
Yes, I do.
Hold on, I'm gonna go get everybody some sweet paper. You have a bunch of paper?
Yeah, I have this
That's
thing.
nice.
But that's like your personal
I
stash.
have a bunch, it's from like high school, I just have it like left over.
Okay,
There's a stash.
thank you. Oh, you're so kind.
Absolutely.
We thank you for this. Could you pass? Yeah. Give Kara a piece
Yeah,
of her
I
paper.
Yeah, and I've just never used it, but I need it for like all my stuff, I can't stand the little.
I wanted to give you Regis funded paper, but you know, we'll take.
Responsible for this.
Here comes the sweet. Oh, you've got your own. And that's cool. Oh, that's, it's swanky, isn't it? Yes. Thank you, Miss Kara.
Yeah.
Here's your remnants.
Oh, thank you.
Yeah, your keepsake from high school. All right, so what I would like, so on this, part of it is just spit out those definitions of a line with there's like a little detail about the line. So basically, step one is barf out that box that I asked you to memorize. So step one is barf out box. And what was in that box? The equation of a line in C, and also the equation of a circle with center Z naught, radius R. Both those, please. Barf's such a crude word, but lay it on the page. And then to solve completely, put your final answer in the A plus BI form. I did make a nice one, a very special one for my special friends who don't want to have suffering too much. Solve I z squared plus 1 equals 0. By quadratic formula or any means would be great. But please put your answer in rectangular form. That's all I ask. Thank you.
Oh, yeah, you can split, turn it in and split, yeah, please, do not.
I thought I might just watch when you're like taking notes or something. So you're like, alright, time
I
to.
was taking notes about you, just writing down everything you did.
He's still staring at me.
Yeah, thank you.